So this is my group. Now we have one full professor, 2 associate professor, and 2 postdocs. Some are like 42 graduate students, which I think is for now is going to be quite some size here. So we are developing this new energy, hydro and some other solar power, but still the thermal power is the major component for the energy sector here. And with this, we have invested a lot, tremendously, on developing matching materials, in particular with the heat resistant materials. And everybody knows this diagram that we are essentially driving the Carnot cycle to increase the efficiency here. And right now, we are in this corner, and we were moving up to this above 700 C and above 28 megapascal, and to achieve this more than 45% of heat efficiency here, and which is essentially driven by the alloy development here. And the heat resistant steels as one of the major materials used for the thermal power generation sectors. We are essentially improving chrome or optimizing chromium and moly addition to get a whole spectrum of alloy derivatives here. And due to their good mechanical properties and oxidation resistance, corrosion resistance, so that's essentially the entire historical perspective of these chrome moly steels here. They are used very heavily for these pressure vessels and pipelines for the thermal power plants. So in general, we divide this the history with regard to the thermal history into 3 major segmentations. One is as received, what I got from the steel plant, that's whether that they are in plate or in pipe, that are defined, and you have to do the welding, and finally that is going to be in service. That's going to be a non-equilibrium condition plus with the final service state. So what we are aiming at is to look at the non-equilibrium phase transformations that will lead to the heterogeneous microstructure of the welded joint. And when in service for these kind of steels, the major concern is on the Crip resistance and how long that will serve and what pressure and at what temperature, particularly for the weldment here. So the key issue for this along the past quite a few decades that people are puzzled by these cracks, and they are generally defined into 4 categories. One is the one they call it type 1. They're generally horizontal. They are not going to be transverse. And type 2, type 3, and type 4. For now, type 4 cracks, they are the most challenging one because they are elusive. It's not so easy to identify them, and also it's not so easy to associate with their appearance with the final mechanical properties. So we are essentially driven by this microstructure evolution in the HAZ, heat affected zones, of this heat resistant steel during the welding. So people actually have done quite a lot of work in terms of interpreting these phase transformations occurred during that circles. And people have used different techniques, and the most recent one is on the high energy XRD X-ray diffraction and also with neutron diffraction to understand how these phase transformations would occur and to what degree and in a way which are going to help assist for the final microstructure development there. So the remaining question challenge is that we know when it will occur, but we don't know the kinetics, and we want to know how fast and how slow a phase transformation could take place. So with this in mind, we happen to jump into this field, and we were inspired by one of the very early students within my group, Mr. Zhou Xiaodong. He was actually studying the effect of the inclusion on the acicular ferrite formation. And we used the confocal scanning laser microscope to understand how one inclusion here in this figure A, number 1, and how this inclusion would induce the acicular ferrite formation and how fast it can grow. And to our greatest luck, we are able to capture the growth of one acicular ferrite, and we were able to capture that cooling rate function as against or as opposed to this acicular ferrite formation kinetics here. So we were able to capture this, and we really want to see because this acicular ferrite, they are not too much different from the bayonet or martensite for the heat resistance steels. So we want to translate this technique into the heat resistant steels, and we move forward with that. And the raw materials used here is actually on these 3 major heat resistant steels, P11, 22, and P91. And as you can see, they are essentially differed from each other by chrome and moly content there. And we all source these raw materials from one major player in the Chinese market. And here are the heat treatment history for these 3 materials. One is P91, 22, and 11. They have very prescribed heat treatment histories here after the normalization, the tampering for this one. There are standard procedures, and we use confocal scanning laser microscope, which I think Warwick WMG has one. I don't remember in which building, but I believe you have one, and you have very good video clips of the dendritic growth of one low carbon, low alloy steels, and they're going to be very useful. I think when I saw that video in 2019, when I was in the lab to see the details of WMG experimental capabilities, and the principles of this confocal scanning laser microscope is very easy. I think many of you have known this one. And what we are doing is actually, we know we are able to adjust the cooling rate. We are able to simulate in this way, which is similar to the heat treatment, to welding. So in this way, we are able to have almost similar, I would say identical heat input as opposed to against with the actual welding here. So we are using confocal scanning laser microscope to track real-time morphology and perform quantitative analysis. Let me give you some examples here. So in the first part, I'm going to talk about more on the coarse grain HAZ, which are generally in bigger dimensions. And what you are seeing here is, for example, in the P11, you are seeing a lot of features popping up when the temperature goes down. In other ways, that as the time goes by, you are seeing a lot of features which are essentially bainite. They are formed, but they are forming in different locations, and they are actually preferentially nucleated in an increasing order of difficulty. They nucleate, they grow on grain boundaries, and also they grow on inclusions here, and also from the grain interior. And since we are consecutively capturing these frames, these images, we have this length, we have this time. Now we are able to, at least in a 2D dimension, to know for one specific bainite, this feature, how fast it can go. And my student did a very good job in placing them into 4 different types for this particular grid for P11. And what you are seeing here after this quantitative analysis, and that these 4 characteristic bainites, they have different growth rate, spanning from about 10 micron per second to about 200 micron per second. So they vary a lot, and we believe that they are associated with a degree of supercoating, which I will elaborate later on this one. So that's one case. That's on the P11 with the coarse-grained HAZ. And we design, or we elaborate on this schematic illustration of how this one goes from high temperature to low temperature. And since we also get the fine-grained HAZ, we want to see whether we are going to have something different as opposed to the coarse-grained HAZ. Now you are going to see a quite different picture here. And after this temperature goes by, you are seeing this bainite growing, but they're growing in a very different velocity, the rate. And in general, they are about a few micron per second, which is much lower than what you're seeing from the coarse-grained HAZ ones. And they are essentially limited by the PIG, prior austenite grain size here. And the growth rate is way much slower than this one. So this is for the P11, and for coarse grain, and also for fine grain. Coarse grain, they have you have a growth rate spanning from about 10 micron per second to about 200 micron per second. For the fine grain, you are having a way retarded growth rate here. And we are moving to P22. What you are seeing going to be having something quite similar, but the idea, the takeaway message is that you are having also an array of bainite formation here, and they are also growing into along different features. One's on the grain boundary, inclusions, and also on the on the tip of the existing or the prior bainite there, so which is B3 and B4. And once done with the quantification, we are able to capture this the ensemble of this bainite here, and they are actually having a velocity differing very much from a few 10 micron to up to more than 200 micron per second here. And when putting everything all together, what you are seeing here, using this illustration here, schematic illustration here, they are having different orientations. They are forming packet. They are forming different length here. So the growth rate of this distinct distinctive bainite layers. They vary from 9 to 200 microns, depending also on the nucleation side of the bainite layers. So that's for the P22 case. And for this, the final one, P91, we actually have a quite different scenario. So the prior two cases, you are seeing the bainite formation, and for this P91, what you are seeing is on the dark ferrite formation here, and which is followed by this gamma cell formation. And after this, you are seeing this martensite formed there. They are essentially inborn with one specific grain, the austenite grain, and their growth rate can also be characterized here, and but in a way much higher numbers. So for these six altogether 6 martensite, their growth rate actually varies from about more than actually 100 micron per second, which is the lowest one, to about 500 micron per second. So our contribution is actually to give some insight, at least to give to share some light in a quantitative way of knowing how fast a bainite can grow and how fast one martensite can grow. And what you're seeing here on this right hand and from A to D is actually the final microstructure that this martensite layers they essentially they are forming the packet there, and they are having very high degree of the Km values there. And putting this all together, what we are seeing here is that we are looking about at the left diagram there. From 1673, you're forming this data ferrite, and you're having this ferrite to austenite from transformation. And after that, you are seeing a whole array of martensite formation there, and they are forming essentially into packets, into blocks, and into which are essentially driven by the individual lathe there. So these 3 cases is actually what we are seeing under one confocal scanning laser microscope. Let me put everything all together. Let's take a look on these video clips there. They are actually to the real time. You can get a sense of how fast and how one martensite can grow. So the martensite is on the right hand side, and for the P91, and the bainite is actually on the P11 and the P22. That what we're talking about. So these clips are on the 1-to-1 real-time clip here. So this bainite growth, and these are also the bainite for the P22. For this P91, what you're getting there is you got a almost instantaneous nucleation and growth of this martensite, but they are essentially confined into one specific grain. But for some cases, you are seeing the transgranular formation of the martensite. So this is actually the the first part of my talk here. The second part of my talk is actually we go further. We know how fast one bainite can grow and how fast martensite can grow. We want to go straight forward to the other challenging issue that is associated with the phase transformation there, which is on this soft zone. Where is the soft zone? And this is actually a very elusive idea. People are talking about this one, but not to a way, to a manner which can be quantified, and which you are not able to give you a very good indication of how and where you can spot the soft zone. So, but the significance of soft zone is very large. That is generally considered the most dangerous part, and is the weakest part because of the microstructure deterioration, which can lead to downgraded mechanical properties, and which is particularly true for Crip cracking. That mechanism is going on. So for this heat resistant steel, this soft zone, how to identify that constitute a very big challenge here. What we have done is actually we design a way to simulate welding, to get the simulated welding as compared to the actual welding. So people are doing the actual welding using different welding techniques, and we are using the Global machine to see whether we are able to enlarge or magnify this soft zone. So the soft zone, as I'm going backward here, is somewhere like within the boundary between fine-grained HAZ and intercritical HAZ. So, but due to the limited size of that, the dimension of that, it's not so easy. Generally, people would fail to identify where they are. So our task is to find a way to enlarge this one by means of simulated welding. And we are going to offer a few key features, including the hardness, the microstructure, and also with this carbide evolution there to see whether they're comparable to each other. So what we have done is on actual welding versus simulated welding here. And what you are seeing on the left, the upper left corner is that on actual welding, here's the how one hardness profile will look like. The HAZ is somewhere like about 2.4 millimeter, and after this simulated welding, and we are able to enlarge this to more than actually 3 times, and we are able to almost in the same way to enlarge each characteristic region, the coarse-grained HAZ, fine-grained HAZ, ice HAZ, and almost triple value to that. And we have a comparison of the microstructure here, actual welding, simulated welding, fine-grained HAZ as compared to the fine-grained HAZ, coarse-grained HAZ as compared to coarse-grained HAZ, and also for the intercritical region there. So what you are seeing there is that we are able to get almost identical, at least a similar microstructure there, and you are having a relatively comparable hardness profile there. And the story does not stop there. Is that we go further with so after this simulated welding, we want to have the post-weld heat treatment to see how this will would alter the properties there. And after this post-welding heat treatment, we are able to for this actually welded part, the soft zone is about 0.45 millimeter, and for the simulated one, which is about 2 times of the soft zone. So in this way, we are able to enlarge the soft zone, which shows the lowest hardness value, which are generally a feature, a distinction that will be regarded as where the soft zone would reside, will dwell on. So in a way, for now, we are able to expand the soft zone in the width dimension. The width length is from 0.45 to 0.75 here, and they are having actually very similar microstructure We are doing the SEM in terms of also with the EPMA on this elemental mapping on the carbide formation and carbide population. They're actually very similar to each other. So we have done this for 6 hours, and we also tried to do this for extended durations for 48 hours, and also for very long one is 480 hours, 20 days for this. And what we are able to characterize to contribute that by using this technique, we are able to accurately position the soft zone, which is in the region from the fine-grained HAZ adjacent to the intercritical HAZ after this post-welding heat treatment. So for 3 cases, we are able to identify soft zone, and which now in a very much extended dimension here. So that is actually what we have done, because we have known the kinetics. We were able to give a way of characterizing the soft zone. And the final thing for us is to give some idea of how in what way that the Crip resistance, that property would behave. So now comes to our final part that I'm going to talk briefly on recent progress with the Crip testing here. Here are the samples we have actually generated, and here is one illustration of how one Crip testing sample was made according to the standard there. And after having this one, we are able to observe the microstructure in a prescribed region, also to the requirement there. On the left side, what you are seeing is on the microstructure there of the actually welded the sample after post welding heat treatment, and also the sample after Crip testing. And here you are seeing a very long crack, which we would say is kind of similar to the type 4 crack there. So we did the hardness testing as a function from the distance from the fusion line there, which is standard measure there. We are able to get to know that after this heat treatment, the hardness is heavily depreciated, and after Crip testing, they are even further depreciated, and the soft zone of the weld joint in the Crip state is identified as in the intercritical in the ICHAZ here. And here I'm going to show a few images of the Crip samples there. We have done accelerated testing, 80 megapascal, 100, 120, and 140 megapascal. And we are able to generate a very standard Crip testing. These diagrams, they are actually following very nicely with this thermal activity process there, and as a function of the Crip stress, Crip time, and also with the for the Crip rupture time there. And to our surprise, amazement, that after this Crip testing, and as I have shown you a few slides ago, that we have seen these cracks, and now you are seeing a enlarged version image of the cracks, and we want to know what they are, and we go further with this crack characterization, and we found out that around these cracks, they actually have a very high volume or number density of this carbide. They have been formed along, or they have been found along these cracks, and they are heavy in chrome, and they are actually heavy in moly. So we believe that these cracks are essentially driven by the carbide formation along this intercritical HAZ, this region, and these cavities and the large cracks. They have been formed in the ICHAZ. So let me summarize here, give you a quick summary of what I've been talking about over tonight, over the past one hour here. We have elaborated on the three very typical heat resistant steels, P11, P22, P91. And we were able to capture their featured phases, which are bainite and martensite, respectively. Bainite for P11 and P22, and martensite for P91. And the other thing is we have done is that we were able to offer one technique that would help to identify the soft zone, and after using this technique, we were able to understand the Crip cavity formation along these cracks. How well you are applying this 2D observation into the real 3D construction there. So thank you very much for reading these questions. It's a very good one. These two are actually connected to each other. And for what we are doing here is actually we are also trying to understand it in the 3D dimension, and we compared the current kinetics, the quantified result, which people have done before, and they don't differ that much from previous papers. What we are trying to understand is that in a 3D, then in the real world, so this either martensite or bainite, they could grow in a way which is not into these categories, into these types, as we have just elaborated in my slide in the papers. But the critical challenge for us is that we know that the 3D particularly for this martensite, in the 3D, they could be impinging on something else instead of just going straight into one grain here. So I don't know whether I'm answering your question directly or not, but at least for now, we are converging this data from 2D to 3D. So I assume that you are going to see another paper by our group in about 6 months or so. Yeah, we are fully aware of this issue, in particularly in converting this 2D and extend it into the 3D model there.